Thank you. Good afternoon, everyone, and I do apologise for speaking English, but trust me, you would enjoy me speaking in French even less than you will today. I'd like to say that it's a great pleasure to be here in Paris, and it's a real honour to be asked to deliver the Coulomb lecture. My lecture is entitled Linking Theory and Practice in Groundwater Control. And I think it's very appropriate that I'm talking about groundwater in France because French scientists and engineers have made great contributions to the practical ways that we analyse groundwater. In my lecture, I'm going to talk about Henri Darcy and Darcy's law. And Darcy's law comes from some work that Henri Darcy did on the water supply to the town of Dijon. But also Jules Dupuy had many achievements, but among those was some simplifying assumptions about groundwater flow, which is still used today to help us make complex groundwater situations simpler and easier to analyse. I'm going to be talking about groundwater control, and I define that as the various techniques which can be used to allow subterranean construction works, such as basements and tunnels below groundwater level, to be formed in dry and stable conditions. And it's relevant to be talking about that in the opening decades of the 21st century because lots of the large infrastructure projects in terms of transportation, energy, water supply and waste disposal involve deep excavations, and groundwater control plays a key part in those. I've put a couple of images up here. The one on the left is from Hinkley Point nuclear power station in Somerset in the UK. The image on the right is one of the many shafts on the HS2 railway in the UK. Interestingly, both these projects have quite a lot of French involvement, both at staffing level, but also at client level, designer level, and contractors. So in my synopsis of my talk, I'm going to continue with some introduction and definitions. Then I'm going to talk a little bit about the history of applications of groundwater control. Then I'm going to talk about theory, then practice, and my conclusions are my thesis that we need to get better at linking theory and practice. So as I've said, groundwater control covers the techniques that we use to control groundwater to allow us to work in deep excavations below the groundwater level. Importantly, groundwater control is part of what we call the temporary work. So in other words, it's an element that is essentially needed to produce the permanent works, but doesn't necessarily leave anything physically behind itself. And I've been doing groundwater control for nearly 40 years now, and I think I've come to the conclusion that lots of people think that groundwater control isn't very important, and I understand why they might think that. Particularly if you look at the cost side of things, studies have been done which indicate that on a large civil engineering project, even one with deep excavations, the direct cost of, say, pumped well groundwater control might be quite a small percentage. Roberts indeed indicated that sort of sometimes less than 1% of the cost of a civil engineering project is on groundwater control. So it's logical to think this isn't a very important thing in the big picture. But I think that's the wrong conclusion. And the reason that I think groundwater control is critically important because of where it sits on the programme, where it sits on the timeline of a project, because it sits right at the very beginning. Because groundwater control is often the first geotechnical process, or one of the first geotechnical processes that must be carried out, but it's almost certainly the first one that must be proven effective in order for the subsequent works to occur. And the problem is that if you get a ground control system that isn't a good match for the ground conditions or isn't flexible and isn't robust, and it needs to be modified, that can cause delays in the overall construction project. And because these delays occur at the very start, it's really hard to recover those delays later on. And of course, the cost of delays is much greater than the incremental cost of making the ground control system more robust and flexible in the first place. So now I'm going to talk about different ground control strategies. And there are three main strategies, different ways of dealing with groundwater. These are the pumping strategy, the exclusion strategy, and the fluid counterpressure strategy. And I'll take you through each one in turn. So groundwater control by pumping is probably the easiest to understand. In English, we sometimes call it dewatering, and it essentially involves installing an array of wells or sumps in or around our excavation. Then you install pumps and you pump from these multiple locations, multiple wells, multiple sumps, and the collective effect of lowering the groundwater level essentially means that you can carry out your excavation in dry and stable conditions. There's normally a requirement then to pump a continuous flow of water, and it might be quite a high flow if the ground is permeable, and then you need to dispose of that water, so that can sometimes be a constraint. So in this diagram, we've got an excavation here, and we have a series of wells around the outside. They pump and they lower the groundwater level. These are some practical examples. Here on the left-hand side, we have a shaft. You can see the bottom of the shaft is dry, despite the groundwater level being quite high here, but that's because there's a series of pumped wells, these blue pipes, around the outside that are lowering groundwater level. This diagram over here is a large excavation in Canada in complex glacial soils, and we have a series of wells that are collectively lowering the groundwater level. The next strategy is the groundwater exclusion strategy, and in very simple terms, we're trying to keep the groundwater out. What we might do is install a physical cut-off wall around the perimeter of our excavation. That can be either a physical wall, or it may be a zone of treated ground that's the way we've treated it to reduce the permeability. In this case, we have to pump much less water. We basically just have to deal with the water that's trapped in the area enclosed by the cut-off walls, plus any seepage and so on. So it has the advantage that we're pumping much less water, and also it has the general advantage that we're probably going to be having a much smaller lowering of the water table on the outside. So if we're worried about impacts, it can have its advantages. This is a picture of a project in the Middle East. It's a deep basement car park. In this case, the permanent work structure of the basement is formed of concrete diaphragm walls, and that's been used as part of the exclusion strategy. We have some blue vertical pipes, which are the pumped wells that are dealing with the water on the inside. This highlights that for the exclusion strategy, sometimes you can integrate this with the permanent works. So if you're building a structure, a shaft or a basement, where you have either steel sheet piles, concrete secant pile walls, or concrete diaphragm walls, then depending on the depth, maybe those permanent walls can become part of a groundwater exclusion strategy. The third technique is what we call the fluid counterpressure technique. This is generally relevant to shafts and tunnels, because in those type of projects you only have a small area of soil or rock exposed at any one time, the tunnel face or the shaft bottom. And the concept of this method is that if we can essentially use a fluid to pressurize that restricted zone, then we can use the fluid to counterbalance the groundwater and avoid groundwater ingress. Typically, fluids that can be used to pressurize this are compressed air, water, or bentonite slurry. This method is the basis of most closed-face tunnel boring machines, or TBMs. This is a picture from the HS2 project in the UK. It's actually the Long Itchington portal. I think this tunnel is completed now. And this is the very long tunneling machine. But here we have the element that deals with fluid counterpressure. This is a view at the end. We have the cutter head here, but behind the cutter head there's essentially a pressure bulkhead, and that means then that there's a volume behind the cutting head that we can pressurize, and if we can manipulate that pressure, we can counterbalance the groundwater pressures. I've described 3 different strategies, but it's important to realise that these strategies can be used in combination, either on one single structure, or maybe if you have a large or a long project, you might use one strategy in one area and a different strategy in the other. This image here shows an excavation that has a perimeter cut-off wall, which is essentially an exclusion approach, but there's some significant pumping going here from deep wells. We're pumping, and then one mitigation measure we sometimes use is artificial recharge, and that's where we carefully and in a very controlled manner re-inject the pump water back into the ground. So in this case here, the pump water has been pumped out, there's a groundwater treatment system, and over here we have a structure that's sensitive to settlement, so we're going to very carefully re-inject the water around that structure with the objective of maintaining the water level at its original level. And I want to talk a little bit about history, because what's interesting is, of the 3 methods I've discussed, none of them are particularly new or innovative, and the origins of each method, even in its current form, can be traced back to the mid-19th century in most cases. I admit there have been considerable improvements in methods, materials and energy sources, but the principles behind the methods remain the same. The early applications in civil engineering for groundwater control probably date from the 19th century, but in mining we've been doing groundwater control for much longer. This is some great illustrations that are actually available free on the web from the 16th century, and this particular one is an exclusion method. You see it's a cofferdam made of timber piles with operatives bailing the water out in buckets over the side. But a cofferdam today would look almost the same. This is a pumping system. So we've got an excavation here, and we have hand-operated pumps to lift the water out of the excavation. as I've said, there have been considerable improvements over the years. So if we look at power sources, for example, here the power is the human being. These are human-powered pumps. As time passed and we got into the 19th century, horsepower, literal horsepower, became more apparent. This is what's known as a horse gin. So over here we have a shaft, and we need to get the water out of the shaft. So in the bottom of the shaft, the operatives bail water into a big container that's attached to a rope. The horse gin is a vertical capstan at the surface. It's attached to one or more horses that walk in a horizontal circle. They wind the rope up, and the water is then hoisted out of the shaft, literal horsepower. In the 19th century, steam power became developed. And if you look at the history of steam power was probably developed, broadly speaking, for groundwater control. The dewatering of mine shafts was one of the primary drivers to developing steam engines. So steam engines we understand today, you could argue, come from a groundwater control origin. This is a picture from a project called the Kilsby Tunnel in the UK, which was built under the direction of the engineer Robert Stevenson in the 1830s, and it's generally recognised as probably the first large-scale application of pumped groundwater control in the modern pattern. What you're looking at here is a series of steam engine houses, and in the foreground there's a pumped well with pumps in it. Just out of interest, that's a horse gin in the background. You can see the horse there and its operatives walking them round in a circle. This is how a steam pump works. Broadly speaking, you have a vertical cylinder that creates a reciprocating motion. There's a beam that transmits that motion there to pump rods and pumps away. Nowadays, we don't use steam power. We would use electrical power or perhaps diesel prime movers. This is a picture of a very large capacity sump pump, electrically powered, that I worked on a project in Canada. And of course, in geotechnical engineering in general, not just in our field of groundwater control, nowadays energy sources, carbon emissions and energy costs are a key part of what we're trying to do. So I'm now going to move on to theory. I'm going to cover three aspects of theory. I'm going to cover Darcy's law, effective stress theory, and the loading effect of groundwater pressures. These are very simple theories, but I do believe that we need to get the concepts right. So I fully admit that the mathematics of groundwater flow can become unpleasantly complex. And in a lecture like this, maybe you're expecting me to discuss an equation like that. That equation is the equation for time-dependent groundwater flow in 3 dimensions, where there are different permeability properties in each of the 3 Cartesian directions. And I'm sure there is a time and a place for that equation, but it is not today. Because what I want to stress is that this equation and all its brothers and sisters are built on some very simple principles. Broadly speaking, they're built on Darcy's law and the principle of conservation of mass. So I want to talk about Darcy's law, because it's so fundamental to almost everything we do in geotechnics that we forget about it. And Darcy's law is the relationship between flow rate Q, in cubic meters per second, flow rate of water through a defined cross-section area A. It's a relation between that flow rate Q and the hydraulic gradient. The hydraulic gradient being a dimensionless parameter which is created by the application of an excess head difference over a flow path method. And hopefully my diagrams in a moment will explain this. So the Darcy's law says that the flow rate Q is equal to a coefficient of proportionality that we're going to call permeability times the hydraulic gradient times the area. The negative term is really important, which is sometimes neglected when we see it published, because the negative term means that the water flows down the hydraulic gradient. And Darcy's law is named after Henri Darcy, and we use it so widely in geotechnical engineering, we forget it's not a geotechnical equation. It comes from public health engineering. So Henri Darcy in the 1850s did quite a broad-ranging study of the water supply to the town of Dijon. And part of his work, the bit that gives us Darcy's law, was looking at the filtration of water through sand columns. And if you go to water treatment works nowadays, there are beds of sand through which water is percolated. So Darcy had this sort of experiment. It's one of his original plates, where he has a sand column through which he passed water and made various observations. And he developed the equation that we know as Darcy's law, that related flow rate to area and to hydraulic gradient. And this is the equation here, and I've said we have this coefficient of proportionality. And the coefficient of proportionality in this equation is what we call permeability in geotechnical engineering. It's sometimes known as hydraulic conductivity. It's typically given the symbol K, and it's expressed in units of velocity or meters per second. And Darcy's law shows that permeability, a parameter he probably didn't quite invent, but created, there's a need for it in his equation. Permeability is a measure of the ease with which water flows through a porous medium. And so higher permeability for a given geometry will result in a higher flow rate. And for the vast majority of geotechnical cases, the flow we observe will be Darcian, which means that on this diagram where we have flow rate on the vertical axis against hydraulic gradient, the relationship between flow rate and hydraulic gradient is linear, and that's what Darcian flow means. And if you analyse geotechnical cases, it's nearly always Darcian. At higher hydraulic gradients, we get non-Darcian flow. What happens is the water becomes turbulent, and therefore some of the flow energy is lost to turbulence. So in that case then, the relationship deviates from the straight line, and it becomes what we call an underproportional relationship, which means that the flow rate doesn't increase as rapidly as you would think with hydraulic gradient. So on Darcian flow, it's important to realise it still means that flow responds to hydraulic gradient, it's just that the mathematics changes. And it's worth saying that you can occasionally get non-Darcian conditions in geotechnical problems. For example, if you've got high hydraulic gradients through fractured rock, maybe around a packer test, you can sometimes get non-Darcian flow. And what Darcy's law does is it tells us that we can control rates of groundwater flow by manipulating hydraulic gradients. That's the key point. The typical way this is illustrated in textbooks is this way. It's in the textbooks I've written has this in, and most textbooks do. And it's some sort of generic version of Darcy's actual experiment, but it's not terribly, informative in the real world. I think this sort of diagram where we're visualising a well is much more informative. So here we have an aquifer, we've got a vertical well, and we have a pump in the well. And what we do is we're going to pump from this well, and obviously we know we're going to lower the groundwater level in the well. This creates an excess head, a lowering of the water level in the well, and that will cause flow to occur towards the well, and we get a hydraulic gradient. And while it's not a precise match, you can visualise the hydraulic gradient as being related to the slope of a water level, a slope of a piezometric level. So how does Darcy's law relate to the various methods I've discussed? For pumping methods, I think it's pretty intuitive and obvious how Darcy's law works. We've got an excavation down here in plan view with a ring of wells around it. This is a cross section. So here we have a well, we're going to pump on it, so we create our delta H, we lower the groundwater level there, and the groundwater is then going to flow towards it in response to the hydraulic gradient. If we pump at a fairly high flow rate that exceeds the groundwater available from things like surface infiltration, leakage from strata, and horizontal flow, then the zone of influence, this area here where there are actually hydraulic gradients, will increase and increase. And eventually, if you pump long enough at appropriate rates, the system would come into some sort of balance, and the zone would no longer continue to expand out. So I think for pump methods, it's easy to figure out how Darcy's law applies. But what about the other methods? And the exclusion methods can be explained in terms of Darcy's law. And if we go back to the basics of an exclusion method, we have a low permeability barrier here, which means that we can pump on the inside, and we pump a much lower flow rate, and we also have very little or no drawdown or water lowering on the outside. What we're actually doing is we're concentrating the hydraulic gradients in the barrier. And then if you applied the mathematical Darcy's law to it, the hydraulic gradient applied across there combined with the permeability of the wall will give you the flow rate. It's also worth noting that looking at Darcy's law in this way tells us that the thickness of the wall is also a parameter, because the thickness of the wall affects the hydraulic gradient. There's the hydraulic gradient now. It's much flatter than the last image. And so, for example, that's why if you compare a physical exclusion barrier for groundwater that's a thin wall, maybe a concrete diaphragm wall, compare that with a thicker zone of treated ground, like maybe a jet grouting barrier, both the thickness and the permeability is relevant. For the fluid counterpressure methods, again, Darcy's law tells us what's going on. Because the point of the fluid counterpressure methods is that we are trying to balance the groundwater pressure with the pressure inside the excavation, so therefore delta H is 0, and if you go to Darcy's law, if delta H is 0, there's going to be no flow. So I would suggest that Darcy's law is a much more powerful tool than we currently give it credit for, because it lets it understand quite a lot of complex scenarios. And now I want to move on to another very simple concept, effective stress. Again, it underpins everything we do. But I'm going to talk about how effective stress is related to groundwater control. So at its very simplest, effective stress tells us that when we load a soil, including by its self-weight, part of the load is carried by interparticular friction between the particles. But part of the load is carried by the pore water pressure, sometimes given the symbol U. So in very simple terms, if we lower the groundwater level, we're going to reduce the pore water pressure, and that's going to increase the stress on the soil particles themselves. Conversely, if by some means we raise the groundwater level, that's going to increase the pore water pressure, and that's going to reduce the load on the soil. But then the additional sort of complication or sophistication is that as well as the effective stress, the effective stress will actually affect the soil strength. We have the Moore-Coulomb failure criterion, and that tells us that the shear strength at failure of a soil is related to effective stress. And so if we imagine a scenario where we're lowering the groundwater level and therefore reducing the pore water pressure, we're increasing the effective stress. So in theory, we're making the soil stronger. But to go the other way around, if we have a high groundwater level, high pore water pressures, low effective stress, the soil will be weaker. And I'll discuss in a moment, if we get to the point where the effective stress becomes almost zero, the soil can lose nearly all its strength. So let's consider the effect of groundwater flow on soil strength. So let's imagine a laboratory experiment that's not very dissimilar to Darcy's situation, where we have a vertical cylinder of sand and we're going to feed water in at the bottom. So we're applying an excess head delta H, we pour water in, continuity of mass tells us the water must come out, and in this situation where the excess head is small, the weight that we sit on top of the sand will probably be stable, because we've got water flowing over the top, but the pore water pressures here won't be too high, and the situation will be stable. But if we change it and we make a much bigger excess head, we can visualize here that the hydraulic gradient in this zone will be much higher than it was previously. That therefore means that the pore water pressures here will be higher, but the stresses, the total stress haven't really changed, so the effective stress here is going to become low. And if the effective stresses become close to zero, the Moore-Coulomb failure criteria tells us that the soil will have very little strength and will become very weak. And in theory, this weight will sink into the ground. And this all sounds very abstract and nice in the laboratory, but it can occur in the field. And what you're looking at here, and I should stress this is not one of my projects, a industry contact of mine sent me this picture very kindly. So this excavator probably weighs about 15 tons, and obviously at some point it's been sat in the bottom of an excavation that has walls around the outside, so the sides are nice and stable, but in this case the bottom has achieved a situation where it could not support the weight of the excavator, which has quite a low bearing pressure anyway, and it's sunk into the ground. And the situation when soil becomes very weak due to groundwater flow is sometimes known as quicksand. And people sometimes use the term quicksand incorrectly as if it were a type of material. It's not. Quicksand and the equivalent running sand and so on are a state within which soil can exist, and that state is related to the hydraulic gradients. So a classic case where quicksand's a risk is where you have an excavation that's steel, in this case say sheet piled, the sides are stabilised, and what we're going to do is we're just going to sump pump from the inside. And what you're doing is you're creating upward hydraulic gradients in this zone. A problem comes, let's say you have a slightly deeper permeable zone, maybe a gravel beneath you, then you're going to get a big concentration of upward flow in that zone. And here there's a risk that in this zone you'll get a concentration of hydraulic gradients, and in that situation, because the total stress is low because you've unloaded the soil by excavating it, you can get low effective stresses and you can get quicksand conditions like the last picture in there. Of course, if we understand the ground conditions, we can prevent this. And so, provided our investigation boreholes have gone deep enough, and provided they've identified that there is a permeable zone here, a pretty obvious solution is to install some pumped wells targeted at the deeper zone, and then you depressurise the deeper zone by pumping. We get the groundwater level down to here, and then we're going to allow this sand to drain down naturally into this gravel which we've depressurised. And here the situation is transformed here, and you get much better working conditions. But again, it does depend on your investigation going deep enough to identify that deep layer. And I want to talk about the third part of the theory, which is the loading effect of groundwater pressures. Because so far I've mainly been talking about situations where we have groundwater flow, and groundwater flow is part of the problem. But you can get groundwater problems where there's no apparent or no significant groundwater flow, and that normally results from uncontrolled groundwater pressures. And one of the classic cases is buoyancy uplift or hydraulic uplift. So this occurs where we're excavating down in a low permeable material. It might be a clay, a mudstone, it might be structureless weathered chalk. But at some depth below us, there is a permeable stratum, and importantly, it has a piezometric level that goes above excavation level. So essentially, we have what we call a confined aquifer here, and then we're going to excavate down without reaching the aquifer, but with we're going below the piezometric level. And so the interesting thing is, if you were to drill a monitoring well within the excavation, it would overflow. And people generally don't drill monitoring wells in excavation because it's very problematic and you don't want it overflowing. But it does sometimes happen. Again, not one of my projects, but it's a fascinating photograph if you can see it. So we've got an excavation that comes down to here, and it's supported within concrete diaphragm walls. The blue vertical pipes are pumping wells because there must be a shallow aquifer here that's been dewatered. You can see it's been dewatered. This excavator's in the dry. There are operatives working here. But what they've done is they've drilled a pile bore in steel casing downwards, and they must have penetrated a confined aquifer below them. And you can see that this pile bore is overflowing quite aggressively, quite strongly. It's probably good that it's overflowing because this will be acting as an inadvertent relief well, reducing the pore water pressures. But you can see that this does happen. And I could give you many examples where this hasn't been discovered until the excavation actually has failed. And how would a failure occur? So let's look at a sequence of excavation. So we're talking about excavating down through a low permeability stratum, and we're going to stop in that stratum. We're not going to get to the aquifer below us. But we need to remember that the water pressures in this confined aquifer act upwards on the bottom of this clay plug. So we excavate down part of the way, and at this point the excavation is still stable because the weight of this clay plug here is more than sufficient to counteract the upward groundwater pressures. We would say this has a global factor of safety greater than 1, and it's stable. But as we go down deeper, this plug is going to become thinner and thinner, and eventually a situation will occur where the weight of the clay plug is insufficient to resist the upward groundwater pressures. We would say that the global factor of safety is less than 1, and then there'll be some movement and heave. This clay will probably rupture, and then we'll get a uncontrolled inflow of water. And in English we would call that a blow or an inrush. There are often various colourful words for it. Again, if we have good investigation, this is easy to solve. If our boreholes have gone deep enough to identify this confined aquifer is there, we can install, in this case, a series of pumped wells into the aquifer. We lower the piezometric head, the pressures are reduced, and now if we do our global factor of safety on this using the lowered pressures, it's stable and no problem occur. But when we do analysis, sometimes we think, well, the clay plug has some strength. What can we do? How should we apply the strength of the clay plug in these calculations? Because in theory, you can apply some of the soil shear strength to that clay plug to show that something will be stable even when the groundwater pressures are high. And some really interesting modelling was done by Hong et al., and they used finite element modelling to look at the failure mechanisms of different widths of excavation in this case. And so here they looked at a case, they called it a narrow case, and that's where the width of the excavation is less than 4 times the thickness of the soil plug. And they found that the failure mechanism was in this geometry, this soil plug essentially failed as a rigid body moving upwards, so you had defined shear planes on either side. And they found that in this case that the soil shear strength did contribute. And they figured out that when you looked at global factor of safety based on weight alone, then that sometimes the excavation could be stable with global factor of safety as low as 0.7. But then they looked at wider excavations, and they define a wider excavation as where the width of the excavation is more than 4 times the thickness of the soil plug. And they identified that in this case the soil plug acted as a beam and was subject to bending and rotational movement and horizontal strain. And this meant that the undrained shear strength of the clay plug didn't really contribute to the failure. And in this scenario, even when you allow for the soil shear strength, basically the excavation was failing at a global factor of safety of 1 based on weight alone. So what should we do about trying to apply soil shear strength into these calculations for basal failure? Because the modelling of Hong et al. Does show that for narrow excavations, the soil shear strength does contribute. But conceptually, in order for that shear strength to be mobilised, there needs to be some upward movement. And I think that makes this a very problematic case, because if you need upward movement before the excavation will be stable, that makes constructing, the bottom of a basement or the bottom of a shaft at precise level very difficult. So my general recommendation is that I don't like to use any significant proportion of soil shear strength in the factor of safety calculations. I would normally want to be basing the calculations purely on soil weight alone. So that was theory. Now we're going to move on to practice. I'm going to talk about how we can set objectives for design. I'm going to talk about conceptual models. I'm going to talk about the performance limits of the various techniques. And I'm going to talk about ways we can try and select appropriate parameters, particularly permeability. So with any design or any system, you need to have an objective. What are you trying to achieve? And groundwater control systems, the vast majority of systems, pump groundwater in some form. And if you think about things like Darcy's law and other mathematical equations, broadly speaking, a ground control system is a seepage problem. We're going to analyse it but either in spreadsheets with Darcy's law or maybe a numerical model. So it's easy for a designer to consider that success in ground control design principally results from success in seepage analysis. That an accurate seepage analysis will give you a good design. And I don't think that's the case. That generally speaking, precision in the outcome of seepage analysis is not a key predictor in the success for ground control design. And that's quite a strong statement, but I want to share with you how I've come to that conclusion. So this diagram that I'll discuss in a minute is based on some work I did with Professor William Powery more than 30 years ago, when what we did was we got 20 actual construction projects where ground control using pumped wells was being carried out. It was generally work in soils of low to moderate permeability, so silts and silty sands, and pumping was either by well points, deep wells, or ejector wells. And each dot on here is a particular project. And for each case, we worked out the required flow rate, what we call our calculated flow rate, QC, which is on the vertical axis. And we worked out the QC, the calculated flow rate, using standard closed form equations like the Dupuy-Forsheim equation. We developed a sound conceptual model, and then we used parameter values that we selected carefully. And then we went into the field and we recorded the flow rate. So this diagram, this is the recorded flow rate that we observed in the field. It's on a log scale in litres per second, so 0.1 litres per second, 1 litre per second, 10 litres per second. The vertical axis is the calculated flow rate that we predicted, and again in litres per second on a log scale. So I'll take you through it slowly. So the blue line is where the recorded flow rate is exactly the same as the calculated flow rate. So in that case, I got our prediction exactly right. And we weren't terribly successful, were we? You can see there's a handful of our data points on that line. If we look at the green line, this is where the recorded flow rate was 1/3 of the prediction. So in other words, that our calculations had over-predicted the dewatering flow rate. And so the green line is where we'd over-predicted by a factor of 3. The red line is where the recorded flow rate is 3 times prediction. So in other words, we've underestimated the flow rate. And the first thing to see is that the vast majority of our cases fell within this factor of 3 times greater or 3 times less than the actual recorded flow rate. Interestingly, probably more of them are a situation where our calculations over-predicted the flow rate. And it's interesting, I wonder whether our natural conservatism in picking parameters and characteristic values means that in dewatering, and we're naturally going to be overestimating the calculated flow rate a little bit. But the point I want to make is that most of these projects within this zone were not disasters, that they worked fairly successfully, whereas it's the ones outside that were more problematic. So this showed that even when we applied high standards of conceptual modelling, design and parameter selection, the best that we could achieve was to get our dewatering flow rates within a factor of 3 times less or 3 times more than the actual flow rate. And that doesn't sound great, but the point is that within those projects within that range, there weren't major problems. There had to be some minor modifications to the system, but essentially we had our seepage analysis were accurate enough not to cause problems. The few cases outside here, and on the original paper, they even merited getting a number so that you could refer back to them. They were worth discussion because there were problems on them. But it does show how that precise seepage analysis is not a prerequisite of success. And I don't want you to think that I'm implying that it's unnecessary to try and carry out a methodical and rational seepage analysis. My message is designers should avoid assigning undue precision to their calculated values of pumping rates and so on. My recommendation is the design process should identify the most likely value for calculated dewatering rates, but should also indicate the likely maximum and minimum values of pumping rates. These maximum and minimum values are important because they can usefully be compared with the capabilities of the different systems to confirm that the selected system will be able to cope with the entire probable range of values. So I think a more useful set of objectives for design of ground control systems is to estimate the credible range of pumping rates to support decision making, to help you with the choice and sizing of appropriate methods. And also, one thing I'm not mentioning in detail is in many cases you need to apply for permission from the environmental regulatory bodies, from local government for example, to pump water and discharge water, so you need estimates of flow rates to apply for those permissions. There's a strong argument that successful ground control design should not focus on minimising the cost or even attempting to develop a lean and efficient system. A better plan is to develop a robust and flexible system that can quickly and easily be adopted. And that's because if we have a system that's robust and flexible, that will avoid delays in the project, and the cost of making a system robust and flexible will undoubtedly be much less than the cost of any delays. I'm now going to move on and talk a little bit about conceptual models. And so just to be clear on what I mean, a conceptual model is defined as a simplified, non-mathematical representation of a groundwater system to help us understand and communicate groundwater conditions. So for our type of projects, a conceptual model might include the presence of aquifers and aquitards, permeability values, groundwater levels and how they might change, and hydraulic boundary conditions. And a credible conceptual model is an essential part of any assessment of groundwater control. I'm a great believer in that you should have a conceptual model from the very start of a project. You shouldn't wait until you have a design. So for example, I like to have a conceptual model to help direct the actual investigation, because if you think there might be multiple aquifers, then your investigation would need to try and confirm that in that case. And obviously as more data becomes available, your conceptual model should evolve. And just like with seepage analysis, a conceptual model need not aim for true precision, and in practice you can't achieve that because the data will be incomplete. The aim should be to develop a model that aids the understanding of the problem being addressed based on the data available at that time. And as the design progresses, then more data comes in and you should evolve your model. So I want to illustrate this via means of a case study. It's a project in the UK where there were damaging settlements when groundwater control was carried out. And these cases are actually quite rare when you get genuine damaging settlements, so it's worth a discussion. It's quite a small project, a simple project, and I'm fairly sure that at the time it was done there was very little design and certainly no conceptual model. So it was for a water project where a fairly modest excavation was being made, and the ground conditions were a few metres of soft clay and peat over sandy gravel. So here, this dark soil, this is the soft clay and peat that's been excavated with a frighteningly steep slope. Again, not one of my projects, I was involved afterwards. There's pumped well points here that are pumping from a gravel aquifer that starts about here. And within 3 weeks of pumping, owners of properties up to 500 metres away reported damage. Not settlement, I mean actual damage. And it's really unusual to get damage out of that distance. And you can see here, this is a masonry wall, and there's quite a large opening in a crack down through that wall there. And when we developed a conceptual model at the problem-solving stage, it became apparent that there was a layer of soft, normally consolidated peat and clay near the surface. It was below the groundwater level. The sand and gravel underneath formed a confined aquifer, so when they lowered the groundwater level, that's going to cause downward drainage and consolidation of the peat and clay, and 3 weeks was long enough for the settlement to occur. And it occurred out at quite a long distance from the site. And a conceptual model would have identified this was a risk, I think. What is unusual is that the large zone of influence probably indicates that the aquifer is what we call bounded, which means that it doesn't have much water availability. So when you pump on this, you have an unusually large effect on groundwater levels, and it means we have the groundwater lowering extends a very great distance outwards. And what's interesting to note is that the most distant properties at which settlement was noted coincided exactly with the edge of the peat deposit on the geological map of the area. So in the UK we have the British Geological Survey which produces maps of the area. So you could argue that without drilling any boreholes on site, the geological mapping that was available in the public domain should have directed people towards possibly figuring out that there was a problem. And I think a good conceptual model, or in this case any conceptual model at all, given that I don't think one existed, would have allowed the risk of potentially large consolidation settlements to be identified at an early stage. And I want to talk about the performance limits of the different ground control techniques, because I think it's important that a designer has an understanding of the practical limitations of the various ground control techniques. I understand that depending on your organisation and so on, not every designer has the opportunity for practical experience, but there is published guidance available to give you some indication of the performance limits, because the designer must be aware that not all methods work for all combination of ground conditions and construction requirements. And selecting the appropriate technology is a key part of a successful design. And it's important to realise that you can get different results with apparently quite similar methods. So I'm going to talk about the pumping methods purely at the moment. I'm going to talk about the difference between open pumping and pre-drainage. Open pumping is shown here, and it's the simplest form of dewatering, where essentially we pump from within the excavation. And it means two things. It means we can't lower the groundwater level in advance of the excavation, and it means that, broadly speaking, we're drawing groundwater towards the excavation. So here we've got an excavation supported by sheet piles, and we have a sump that's pumping water. This is what it looks like in practice. Here you're looking into the bottom of a large shaft. This is in London, so this stratum here is called the Thanet Formation. And you can see here that they've got a sump and a pump in one corner. And this appears to be even quite good working conditions. I suspect here the diaphragm wall around the outside is a key part of the success here, because that's acting as a groundwater exclusion barrier. The alternative pumping method is pre-drainage, and that is where a series of pumped wells are normally installed on the outside, and it means we can pump on these wells and we can lower the groundwater level in advance of excavation, and broadly speaking we're drawing the groundwater away from the excavation. This is what it looks like in practice. Here's a small excavation inside steel sheet piles. It's only been dug down to 1 metre. It's going to be dug down after the photograph. But see here we have pumped well points around the outside, pumped by a pump there. And it's really important to understand that in some conditions you can get dramatically different results for the two types of methods. A few years ago, my colleague Toby Roberts had the opportunity to compare two excavations that were in very similar conditions but were dewatered in different ways. So a bit of background, this is a project where two shafts were constructed. I think they're about 200 metres apart in very similar ground conditions of fine sands with a high groundwater level. Both shafts had their perimeter was what we call a contiguous pile wall. So these are piles that do not intersect. There's a small gap between them, unlike, for example, the Seacamp pile wall. And this shaft here was constructed by open pumping. And you can look down and you can see got the pile wall, there's a sump pump there, and you can see that in theory, this is dewatered, it's not flooded, the excavator hasn't completely sunk in, but you can see that the water around the pump is dirty, so that's going to be a problem when it's disposed of. The operatives here don't look like they're having a lot of fun from this. Water's flowing in between the piles, there's lots of slurry and mess. It doesn't look very efficient, does it? This shaft over here is in the same ground conditions, and what you can't see is out of sight, because they're outside the excavation, there's a series of pumped wells that have been pumped to lower the groundwater level in advance. And you can see here that there's a dramatic difference in the working conditions in the base of the shaft. And obviously, between the two cases, the pump dewatering rate is probably almost the same. In the plan it will be both shafts have been dewatered by pumped ground control systems, but the difference in methods gives radically different conditions. And I would choose this one every time. It's more efficient and I think will save the project money. So if you don't get a chance to get personal experience of ground control methods, there is published guidance. In the UK, some of the most widely used guidance comes from a report called Surrey Report C750 that includes a version of this diagram, and I'll go through the diagram in a minute. This guidance was originally developed more than 30 years ago by Toby Roberts, based on project experience from the 1980s and the early 1990s. This version shown here is actually something that we produced just a couple of years ago in 2023, and it's an update based on further recent project experience to better reflect modern practice. So I'll just take you through this for a couple of minutes. So it relates permeability to drawdown. So permeability we've talked about. So permeability is a measure of the ease with which water flows through soil and rock. It's in meters per second on a log scale. So 10 to the minus 7 there, 10 to the minus 7 meters per second. That's a silt perhaps. Up here, 10 to the minus 3 meters per second, that's a coarse gravel perhaps. Drawdown is the amount of vertical lowering of the groundwater level. So from 0 meters, 5 meters, 10 down to 20 meters. So in very simple terms, if we lower the groundwater level by 5 meters, that will be a drawdown of 5 meters. And what this diagram does is it identifies the primary primary range of application of the different methods. So for example, single stage well points, which quite commonly used technique. This identifies that, broadly speaking, they're for drawdowns down to around about 5 meters. You get a little bit less drawdown if the permeability is low, and they're broadly applicable from 10 to the minus 7 meters per second up to maybe 2 times 10 to the minus 3. As another example, the deep well method, which is where we have a bored well with a submersible pump, that they operate in a rather narrower permeability range and greater drawdown. Now, this diagram does not remove the need, there are other diagrams available in other publications, this is one I'm familiar with. These diagrams do not remove the need for a detailed ground control design, but what the objective is that they let you, at the very early stage of a design, identify the most likely forms of ground control methods, and that can help you direct your design and direct your investigation further. And generally speaking, if you're looking at whether you should choose one method or the other, and you've got its range of application, if your proposed method can easily be adapted to handle the maximum minimum parameters, then that's probably going to give you a robust and flexible design. However, if the maximum minimum parameters mean you might need to change the method, then maybe you've got a problem and you should maybe revisit the method you've selected. So now I'm going to talk about the challenges of selecting appropriate parameters. It's worth saying that I deal with a lot of problem jobs. Some of them are jobs that I've been involved from the start and we've had to deal with uncertainty. Other times I come in late to a project trying to solve a problem. So I've seen many problem jobs. And in my experience, lots of the problem jobs in ground control, the root cause is either an inappropriate conceptual model, perhaps people don't understand where the groundwater is and so on, or it might be the use of a ground control method that's not appropriate for the groundwater conditions. But there are some cases where parameter selection has caused major problems. And the most obvious parameter to talk about is permeability, also known as hydraulic conductivity. And we've discussed permeability, and permeability is the coefficient of proportionality in Darcy's law. And in simple terms, it's a measure of the ease with which water flows through soil or rock. And it has a very large range in natural materials. So if we have a high permeability material, such as gravel, sands and so on, that could be as high as 10 to the minus 2 meters per second. In natural soils at the other end, we have very low permeability, and with clays and silts, and we get down to 10 to the minus 12 meters per second. And so natural soils have a range of permeability of probably more than 10 orders of magnitude. I don't think there's any other geotechnical parameter that has remotely the same range. And that means that designers are often faced with permeability data sets that contain very wide range of values, perhaps 2 to 3 orders of magnitude. And that's after you've removed some of the outlying values that you just don't believe. And some of this variation results from the natural variation in the soils themselves. It also can relate to variations in the way that we measure permeability. And I want to talk about the effect of scale, the effect of size on permeability measurement. So we have Darcy's law, and the point to realise is that Darcy's law shows that permeability cannot be meaningfully associated with a single point. It has to be associated with a volume, because Darcy's law contains an area term and a length term. when we combine those, it shows that, like in this diagram here, Darcy's law is essentially about average values averaged over a volume. And the challenge is that natural soils and rocks are not uniform in space. So if we have a volume, that volume is going to contain some variation in the properties, both on a horizontal scale and a vertical scale. So if we think about soil or rock mass, in English we would say it has a fabric. It means that within it there's a texture or a structure which contains properties of different types. And so if you think about many of the soils and rocks we deal with are sedimentary in nature, which means they're laid down in water. In that case, that means that generally speaking there was some sort of horizontal structure, and you would expect the horizontal permeability to be more than the vertical, sometimes a lot more. Similarly, in rock, generally speaking, in lots of cases, the flow of water is controlled by the fractures, and the fractures will have a set of orientation and intersection and so on. And so depending on the scale of the test you carry out, you're going to get different values. And so we talk about a test volume. If you have a large test volume, you're probably going to intercept a greater proportion of the permeable fractures. If you have a small test volume, you might not. So to look here, if we think of a test in a borehole, this would be a variable head test, what we call a falling head test in a borehole, or maybe a packer test like a Lujon test. That might influence a zone of soil maybe 5 meters across. But whereas if we carry out a multi-day well pumping test where we pump, say, for 5 days at a high rate, that might influence a zone of soil hundreds of meters across. And in these two cases here, if we look, that particularly in the fractured rock, for example, the test zone of a larger scale test is much more likely to intercept a representative sample, for want of a better term, of the permeable features, whereas a small test might not. And similarly, if this small test was over here, where it intercepts features, these two small tests are going to have quite different values. So we found that if you carry out a small scale test and a large scale test, the permeability in a given soil or rock can vary by a factor of 10 times or 100 times between the two tests. And I want to illustrate this via a case history. So this case history is about the HS1 railway in the UK. HS1 runs from central London, from St Pancras Station, to the northern portal of the Channel Tunnel. And on its route, HS1 railway passes under the River Thames, in the Thames Tunnel. And so yesterday I passed through this tunnel, which always gives me a little thrill, because I worked on this project in the early 2000s. At this point, the River Thames is about 1 kilometre wide, and there are two large portals. This is the south portal under construction, and then there's a north portal. And the ground conditions are, there's a significant thickness of normally consolidated alluvial deposits, soft clays and peats. Then there's several metres of sandy gravels called the river terrace deposits. And the piezometry level is up here, so this is a confined aquifer. Then below the river terrace deposits, there's the white chalk group, which, as I'll explain, is quite heavily weathered in this area. This is the structure itself under construction. And the ground control strategy had 3 main elements to it. There was an exclusion element, because the structure has concrete diaphragm walls as its permanent works, and they were deliberately deepened to go through and act as an exclusion barrier in the gravels and also in the upper part of the chalk. Then there was an extensive pumping system to deal with the residual groundwater, and then as well there was an artificial recharge system to carefully re-inject the water back into the ground, because next to the site there was a large petrochemical facility, and we were worried about settlement of these normally consolidated soils. This is an image here of inside the excavation. We have the concrete diaphragm walls out here, the big props. These vertical pipes are the dewatering wells, and this brown stratum are the gravel of the river terrace deposit. And so for scale, this excavator here is sat in the dry, and that's probably round about 10 metres below original groundwater level that we've dewatered, and I think it probably went down nearly another 10 metres later on. And again here, this is the north portal here, this is the sensitive tank farm that's been protected, and this red line are the recharge wells where we're re-injecting the water. So the reason for this case study is to talk about permeability. Let's talk a little bit about the permeability. And the permeability of the chalk was important because that will control the depth of the cut-off walls for the groundwater exclusion effect, and it will also affect the groundwater pumping rate. Now the site is located east of London in the channel of the River Thames. Now, during the Quaternary period, the Ice Age, the ice sheets in the UK didn't reach this far south. They stopped a few kilometres north in Essex. But this area, when the chalk was exposed, will have experienced what are called periglacial weathering, sort of extreme freeze-thaw conditions over thousands of years. And so there's evidence that the top of the chalk is very highly weathered and has become what we call structureless. So any natural structure of the chalk has been disrupted. And that's quite common in several parts of the UK. And so the weathering of the chalk meant that it was expected that the permeability will vary with depth in the chalk. So we carried out quite an extensive investigation programme, and we carried out quite a lot of borehole tests. These are the small-scale tests, both falling head tests and also packet permeability tests, Lujon tests, and these are the data from that. So we've got the chalk here, so the top of the chalk is about 15 metres below ground level, and each of these red dots is a data point from a test in a borehole at a particular depth. And you can see that over the 20-metre depth below the top of the chalk, there's a reduction in the permeability of the test results. This is on a log scale, so what we're saying is over 20 metres depth into chalk, the measured permeability reduced it by a factor of 100, probably a little bit more. Obviously that's a challenge for designers. Another challenge was that as well as these borehole tests, we carried out some multi-day well pumping tests, which gave these results. So here, for example, that's the screen section of this multi-day test, and that's the assessed permeability. And similarly here, we did a test screen deeper. So you see here that on a given site, we've carried out these large-scale tests, and they generally give permeability much larger than in the small-scale tests. Again, a factor of 10 or 100. And I put this up to illustrate the challenges facing designers. You've got the natural geology is telling us that the permeability is going to vary a lot, which is a challenge, but then our method of measurement causes difficulties. So now I've got onto my conclusions, and my conclusion is to my theory that my thesis that we need to better link theory and practice. And I sometimes think that if you think about other geotechnical aspects like stress-strain theory and soil mechanics, there have been many developments during the 20th century in analysis. But in reality, the analysis of groundwater flow at a mathematical level hasn't really advanced in the last 100, 150 years. And furthermore, the methods that we use, most of them are long established, dating back to the 19th century. But despite the fact the theory is long established, the principles and methods haven't changed, we still get, in my experience, frequent problems reported with the implementation of ground control systems, even on major projects where you would expect there to be adequate resources for investigation and for design. These problems can take many forms, including significant failure of excavation support structures, hydraulic uplift of the base of excavations underlain by confined aquifers, and disruption to construction programs caused by the need for modifications and enhancements to the planned dewatering systems. Undoubtedly, some of these problems result from us living in the real world where investigations are not adequately funded and not adequately planned, and for example, your boreholes don't go deep enough and you don't spot as a confined aquifer. And these limitations with investigations often lead to hydrological and geotechnical uncertainties. But I think beyond that, I think some of these problems result from a disconnection, a misunderstanding between the theory and practice of ground control. And I think to better link theory and practice, designers and constructors need to understand the relevance of Darcy's law and effective stress theory, and understand how the way we manipulate hydraulic gradients affects the way that the ground responds. We need to recognise that each of the different groundwater control methods have different range of application, and we should apply those carefully. We need to set credible and useful objectives for ground control design. We need to use appropriate and relevant conceptual models. And I can't stress too much that a good conceptual model is a great start to any project. A bad conceptual model can be very hard to recover from once you get into construction. And as I've discussed, permeability parameters should be collected very carefully. So finally, I'd like to acknowledge that what I've shared with you today is a result of nearly 40 years' experience, and I would very much like to thank my former and current colleagues and organisations. We should all recognise that we all sort of stand on the shoulders of our colleagues and try and move things forward. And finally, I'd like to say that again, what a pleasure it's been to be here today, and what a privilege it's been to deliver the Coulomb lecture. Thank you very much.